Agterberg from University of Wisconsin. He'll talk about uniform composite order from antiferromagnetic order.
All right. Okay, well, so even though I am a co-organizer, I would like to thank in particular Igor and Laria for doing the bulk of the organization. So I didn't have much part of this, and I think it's because of them that this conference is working out. All right, so I'm going to talk about uniform composite order from antiferromagnetic order. And so what I mean by antiferromagnetic order is simply magnetic order that doubles the translational symmetry of the non-magnetic state. I'm also going to talk about composite order, which is uniform. And by uniform, I mean an order which is coming from the magnetic order, that's the composite order, and that's going to have the same translational symmetry as the non-magnetic state. Now, when we first studied this, the motivation was not to study composite orders coming from magnetic orders. And the main reason I present the title this way is because of this conference. But our real motivation was to actually think about a generalization of altermagnetism. So in altermagnets, we have uniform magnetic states. And in these magnetic states, spin up and spin down electrons have different energies. And if you look at that energy as a function of momentum in momentum space, it's strongly anisotropic. So these energies cross in certain places, and it changes sign between up and down as we move around. But one key property of all these altermagnets is that this spin splitting that you see is inversion symmetric. What you see at plus k is the same as what you see at minus k. So we were interested in the question of how can you construct states that have an odd parity spin splitting, meaning the spin splitting at plus k is opposite sign of that at minus k. And the answer is going to be buried in these antiferromagnetic orders, and this odd parity spin splitting is going to be a composite order of this antiferromagnetic order. All right, so the two works that I'm emphasizing is this one here and this one here. But let me turn to the people who did the bulk of the work. So I'm going to talk a little bit about microscopic models for altermagnetism. These are Hubbard-based models. And this is work from my postdoc, Merce Roig. And then when I switch to the antiferromagnets, that is work by UAU. You can find it on the archive. And just last night, I got my first set of referee reports, which look very good for this. So hopefully it'll be published in the next month or so, I imagine. All right, and then here's one of the predictions we make. We have this so-called H-wave spin texture in this iron arsenic material. And so here, red and blue are the energies for spin up and spin down at the Fermi. Or these are the eigenstates spin up and spin down. And you can see that this is odd parity.
Daniel?
Yeah.
Just to clarify, so for ultramagnetism, when you integrate over k, you get 0.
Yes.
Right?
Yeah, yeah. So that's, yeah, exactly.
That's a feature.
Yeah, and I'll show pictures, which makes it a little clearer, but yes. All right, so first let me talk a little bit about composite order and where it has shown up in antiferromagnets. And this is actually very well known in the context of iron-based materials. And actually this is a phase diagram from, I think from Taka's group. Well, he's a co-author for sure. And in this phase diagram, you see this is a barium iron arsenic, and you see three phases. You see this antiferromagnetic phase, you see this electronic nematic phase, and you see this superconducting phase. And now, thanks to Sankit's talk this morning, you can probably begin to understand some of the understanding of where this electronic nematic phase comes from. And to understand that, we first look at this antiferromagnetic phase. And this antiferromagnetic phase has a wave vector pi0. So this is in a square lattice. And maybe you can't see the tips of these arrows all that well. But in the x direction, this goes plus, minus. But in the y direction, it all goes plus. So it's ferromagnetic this way and antiferromagnetic this way. Now clearly, if we have a tetragonal system, pi0 must be degenerate with another state at 0 pi, where the antiferromagnetism goes in the opposite direction. And so you can write down spin density for this, and it's going to have 2 degrees of freedom, 2 spin degrees of freedom, one for this vector q1 pi 0 and one for this vector q2 pi 0. Okay. And as was done years ago, you can write down a Ginzburg-Landau free energy for this, in which you assume some spin rotational invariance. You have an S1 squared plus S2 squared like term. This theory has no S1 dot S2 term because S1 and S2 both carry different momenta, so S1 dot S2 carries pi pi momentum, and the free energy needs to be translation invariant, and that term would not be translation invariant. And so you can minimize this free energy, and I'm going to show free energies like this in very different contexts where the meanings of S1 and S2 are different, but it's going to be exactly the same form. But you can find that one of the states that you find here is this S1, S2, as S1 is ordered, but S2 is not. Okay? And so this is exactly this magnetic state I'm showing here. And you can ask what kind of physical properties this state has. And one of the properties, as alluded to before, is it doesn't just have antiferromagnetism, but it also has this kind of uniform magnetic order. And the way we understand that is we can write down the spin scalar, S1 squared minus S2 squared. And clearly in this state, this expectation value is non-zero. Since x1 is along q, s1 is along pi 0, and s2 is along 0 pi, this thing looks like an x squared minus y squared order parameter, and so it has some uniform nematic order. Right. And then you can imagine a situation where the antiferromagnetic order is destroyed by, say, SO3 fluctuations of the spin, and so you can have a situation where then you go from a high temperature into this electronic nematic phase, and then at a lower temperature enter this antiferromagnetic phase. And so the kind of orders I'll be interested in are like this nematic order, and this nematic order is going to show up, again, in the context of the theories we talked about, which are very different, but we'll be able to generalize this idea to a wide range of materials, I think, and then we'll also be able to talk about a wide range of composite orders, well, 3 particular composite orders, including this odd parity spin textures that I mentioned. Okay, so with that introduction, now let me turn to the motivation of why we were looking at this, and then switch a little bit to the discussion on altermagnetism. So the whole goal in altermagnetism is to generate some spin splitting in momentum space. In particular, you want to generate this spin splitting without spin-orbit coupling. So you want it to, and because it's not from spin-orbit coupling, it can be large. But the first thing we have to ask is, what is the source of spin degeneracy in all our materials? And that source is actually time reversal times inversion symmetry. All right, so if we have time reversal times inversion symmetry, we will have a double spin degeneracy. And it's easy to see why. Time reversal flips spin, but takes momentum k to minus k. Inversion takes momentum k to minus k. So the product of time reversal inversion takes k to k. And if we square that for a fermion, it squares to minus 1. That's an anti-unitary operator that squares to minus 1, so it guarantees we have a twofold degeneracy. And so we have this twofold spin-like degeneracy at each k, and so if we want to get a texture, we need to break this symmetry. And there's 2 ways we can do this. The first is we can break time reversal and preserve inversion. This gives us, well, ferromagnets, but it also gives us altermagnets. And so here's exactly an answer to your question. A momentum spin splitting cos kx minus cos ky, which would correspond to preserving this inversion and breaking time reversal. Right. And so here's a picture. Basically, spin up and spin down have different Fermi surfaces. And then you have a point where they're degenerate, so there's some sort of spin nodes there. The other way we can generate a spin texture is by breaking inversion and preserving time reversal. And this will give rise to odd parity magnetism. And so here, the generic example for that we're all familiar with is Rashba spin-orbit coupling. So Rashba spin-orbit coupling is odd under momentum k goes to minus k. And this is going to be the odd parity textures that I'm interested in generating, and for which we have some microscopic theories for. But I'm going to go first through altermagnetism and tell you about some of the theories we have there because they're very closely related. Okay. So
can I think of it? The second case is like spontaneous Rashba? Is that how-
Yeah, like exactly like spontaneous Rashba. And again, the key will be there's no relativistic terms that give rise to this, and so it's going to be, in principle, could be a large spin split.
And you cannot get spin orbit scattering spontaneously without relativity. Isn't that correct?
No, this will, in exactly, so no. Yeah, and I'll show you why later. Okay, so, let me more formally introduce the word altermagnetism. I think, like many of you, when this was introduced as a term, we're kind of skeptical because we feel we know everything about magnetic space groups, and so how can there be a new class of magnetic materials? And so strictly speaking, when this term was introduced, there was a new problem solved. And really the new problem solved was in the limit when we don't have any relation between spin rotations and space transformations, then you can classify all possible collinear magnetic states. And you find there are 3 of them, and this problem actually hadn't been solved before. And so those 3 states that come out, and by the way, here's an example of where spin and space don't have the same rotation. I have 2-fold in spin, but 4-fold in space. And that's relevant for this particular altermagnetic state here. But the 3 states that come out are first a ferromagnet. And a ferromagnet has a uniform in momentum space spin splitting. So this spin splitting between up and down is the same everywhere. You have an antiferromagnet. An antiferromagnet has no spin splitting. And then the last state is this altermagnet, where again you have a spin splitting, but it has these nodes in it, and it's and it changes sign as we move around. Okay. And the key point, but honestly, I don't think this was that interesting a result. It is new, and it lets people make the claim they found something new. But I think more interestingly was there were 2 aspects of this that were pointed out that are relevant for most of the current interest. The first is that its energy splitting is not from spin-orbit coupling. It's because we have no spin-orbit coupling here, so it can be large. And then the second aspect that's important is that there are many, many materials that fall in this class. And so we can start studying these materials, which in principle have these large spin splittings. And so here I show you sort of a DFT calculation of spin splittings across a whole series of materials from the MAGN database. It's published here. Even though the spin splittings here vary from something like 20 to 100 MeV, it's been observed to be as large as 300 MeV, so a very large energy scale. And again, because, in this talk I'm not really motivating why we're interested in this, but because we have momentum dependence in the spin splitting, this turns out to be useful in generating spin currents, and that gives use to spintronics. Right, and I usually give examples, but here I want to get to the parts I want to talk about that are relevant for this conference. All right, so that was the situation maybe a year or so ago. But then more recently, people realized that, well, we don't only have collinear states that come from not having spin and space coupled. You can kind of classify all sort of magnetic orderings in sort of magnetic spin space groups and decouple spin and space and say what kind of other spin textures can exist, what other kind of magnetic states exist. And this was done in 3 PRX papers last August. And the upshot is there's something like 66,000 of these spin space groups. And indeed, you get other spin textures in general, not just the altermagnetic texture, but you also get these P-wave magnets where you find coplanar magnetic states. And so here these spins are orthogonal to each other but lie in the same plane. But in these P-wave magnets, the spin splitting is like this Rashba spin splitting. So here again, we have minus spin and plus spin, and you can see if I go from K to minus K, there's a sign change in this.
Daniel, just a quick question. So do these odd parity magnets, are they a separate entry in the classification of these nonlinear spin groups?
Yeah.
Non-collinear spin groups?
No, they're different than the collinear space groups because they actually involve non-collinear states.
I see.
And so, yeah, I'm not really emphasizing that, but the states I'll look at turn out to be these non-collinear states.
So you're saying basically if you allow it to be non-collinear, there are more than 3
yes,
types? Right?
Exactly. And yeah.
Okay.
Much more than 3.
Oh, okay.
Okay, so now let me tell you what we do. We wanted to develop sort of minimal Hubbard-like models for understanding these spin textures. And we started with altermagnets, but then it turned out the same class of models lets us understand these odd parity magnets as well. All right, but before we do that, it's useful to ask if people had developed models before this. This is Kanjin Wu, who was meant to be here, so I thought it would be nice to put his picture up. But already in 2007, he was the first author of a model for this. And the idea for these models was that you start with a single band Fermi surface. Up and down electrons are degenerate, so you have two degenerate Fermi surfaces. But then you can have what's known as a Pomeranchuk instability, where the Fermi surface deforms. But that deformation can be different for up and down electrons. And then you can get a situation where you go from this doubly degenerate dashed line to this ellipse for spin up and this ellipse for spin down. But this is exactly the altermagnet I was showing you before. So it's no different. And again, this is a spontaneous deformation of the Fermi surface in these pictures. And so the spin splittings can be large, and so they're non-relativistically generated. And so this satisfies all the criteria for a minimal model for altermagnetism. So in trying to develop sort of Hubbard-based models for this, it's actually not so easy to understand interactions that will allow you to get this particular Pomeranchuk instability as opposed to the usual Stoner Pomeranchuk instability that gives us ferromagnetism. And so, so in our models, we're trying to find a different way of coming up with these altermagnetic states. And the one key difference between the models we study and the models studied in 2007 is in these models here, in the Pomeranchuk instability, the spin splitting is actually the primary order parameter. It is what drives the transition, and so it's the primary order parameter.
Danny?
Yeah.
So like when you have spin orbit, let's say Rashba, there the wave function itself is a function of k, so it's an eigenstate of helicity.
Yeah, yeah.
And so then it kind of continues as a function of k, rotates from up to down.
Yeah.
So I'm wondering whether here this picture is a cartoon and really there's a continuous wave function as a function of, as you go, let's say, azimuthally in k space?
So I think I will come to the answer to that, but so I say it's like Rashba, but Rashba involves two spin components, sigma x and sigma y.
Right.
And the states I'll be talking about involve a single spin component only. And so I think that begins to answer your question.
Okay, so maybe it's different. Okay.
It is different. And so maybe Ising spin orbit coupling is another way to is more accurate.
Daniel, just a short question. I still understood it in such a way that for altermagnet it's important that you break the symmetry already in the normal state, that you have two atoms already in a unit cell. That will be very different from...
Yeah, and this is exactly the kind of Hubbard models we're looking at. So, yeah. And this is also pointed out by Libor and co-workers when they introduced the term. Yeah, and so our philosophy then is that the spin splitting is not the primary order parameter, but rather it's a secondary order parameter, and the primary order parameter is antiferromagnetism. And then when we have Hubbard models, it's easy to get antiferromagnetism. And so just to show you how this gives rise to altermagnetism, I've just shown you a simple example here. Okay, so as I mentioned, altermagnets preserve translation symmetry, and so we can define some order parameter for it that has some spin vector part, and that's uniform. That's the same for all magnetic states. But what differs different states then is the spatial symmetry of that. And so if we want to create an altermagnet, you can see right away that it's not enough, so it has to preserve translation symmetry. We can't have just one magnetic ion per unit cell. So here I have a standard square lattice with one magnetic ion per unit cell, like for example, copper and cuprates. And then here, if I want to make a magnetic state, the only possibility is a ferromagnet. And then the symmetry of this gamma n is A1G because this is invariant under all the rotations of this, ignoring the spin rotations, right? And so if I want to make an altermagnet, then, okay, and this is the spin splitting. Let me jump ahead. If I want to make an altermagnet, I have to consider different, at least two magnetic ions per unit cell. And we can classify this in the same simple copper lattice by using a different Wyckoff position, a Wyckoff position of order 2. That means multiplicity 2 in the unit cell. And then I can write down a state, well, I can write down a ferromagnet here, and that's going to be the same, but I can also write down an antiferromagnet, up, down, and this thing is now also translationally invariant, and this is actually going to be an altermagnet, and the difference between this and this is this particular gamma n here is B1G, not A1G. Okay. And then the site symmetry here is D2H. So this is like the oxygen in the copper-oxygen lattices, right, if we're familiar with cuprates. And in fact, you can see how this symmetry, twofold rotation by twofold rotation spin by fourfold rotation in space, is invariant here. So a twofold rotation just flips blue and red, but then a fourfold rotation by this axis also flips blue and red, and so that's a symmetry of this state. And so this is really one of these spin space group symmetries in this case. And then you can also show that this symmetry guarantees that we have this kind of cos kx minus cos ky spin splitting. In particular, if I go along the x direction and I get some spin splitting, then I rotate by pi by 4, a fourfold rotation. That'll take me to the y-axis, but I have to flip spin for this to be a symmetry, and so I must have the opposite ordering along the y-axis. And so you can see that these states have, well, these altermagnets have no magnetic moment, in principle of large splittings, and have these nodes in delta. Okay, so that brings us to the kind of class of Hubbard models we've been studying, and I'm not going to spend too much time on this, but other than tell you we have a class of microscopic models. And what we did was just identified all space groups with Wyckoff positions of multiplicity 2. So we have a two atom magnetic sublattice. We required all the Wyckoff site symmetries to contain inversion symmetry, because that guarantees our spin textures don't break inversion symmetry. And then we add all on-site Hubbard terms on these two sublattice, and we also add all tight binding terms that are allowed by symmetry. And then with these models, we can then use RPA to search for magnetic instabilities. And then you can find altermagnetism as a zero momentum instability in here. And so I'm not going to go through the details, but we're able to explain a few aspects of altermagnetism. We can explain the origin of the altermagnetic spin splitting, and that's exactly what you were saying in the back. It's coming from a normal state term. We can explain why non-symmorphic crystals turn out to be better than symmorphic crystals for stabilizing this. We can talk about the role of spin orbit and some other effects.
But can you say there's another order parameter that's degenerative where the locking is by pi, you rotate by pi over 2? In other words, you had in the x direction it's up and then y direction is down, but you can flip the two directions, x and y.
Yeah, so we could rotate between them, yeah. So are you asking about the altermagnetic order? Is that
Altermagnetic order, the example you gave in the previous slide.
Yeah, so, okay.
What about the order parameter where there's also an order that's degenerative where you exchange red and blue?
Yeah, so I think you're referring to another symmetry that I can exchange red and blue, right?
Right.
Yeah, and then indeed you can show that this texture is also consistent with that symmetry as well.
Okay.
So I think that's what you're after. Yeah, and so here, this is the antiferromagnetism, which is the primary order parameter, and this is the secondary order parameter, is the spin splitting in momentum spaces. So that's what I was referring to.
Daniel, related to your remark and also Ilias, what do you mean by some symmetry is already broken?
It's not, it's, okay. Okay, what I strictly mean is if you look at these Wyckoff positions, they have lower symmetry than the one in
the
the
site
center of the cell.
symmetry is already lower.
Yeah, so the site symmetry is already lower,
Okay.
and that introduces new terms in your Hamiltonian, and that's what generates the altermagnetism. Yeah, but I didn't really write down those theories here because I wanted to get to this next bit, which is the second part. All right, so when we were studying these models, we don't only find instabilities at q equals 0, we also find that there can be instabilities at q equals pi pi and q equals pi 0. So these are antiferromagnetic states which double the periodicity of the lattice. And so we decided to study these in a little bit more detail. And so here I'm showing you an example so you can understand exactly what we're doing and how this differs from antiferromagnets of the past. Okay, these have existed as well, so I shouldn't really say the past. But again, we're going to have 2 magnetic ions per unit cell. On one, we're going to have a spin S1. On the other, we're going to have a spin S2. But here I'm going to relate these 2 sites by an inversion symmetry that sits between them. I've chosen Q equals pi 0, so here we have one, here I have the spin pointing this way, but then the next has to point the opposite way, right? And the first thing I want to do is just write down a Ginzburg-Landau free energy for this particular situation, and I'm going to assume I have my inversion symmetry here and I have global spin rotational variance. So when you do that, you get exactly the same Ginzburg-Landau free energy I talked about in the iron-based materials. And so we get an S1 squared plus S2 squared plus a series of 4th order terms. And I'm going to be honest right now. It turns out if you listen to what I said carefully, you'll realize that in principle there's another term I can add to this Ginzburg-Landau free energy. And that term actually ruins a lot of the physics I have, but I'm going to later explain why that term doesn't show up. And I'll let you think about that term and see if you can figure out what it is. All right. But okay, we have these quartic terms. You can minimize the free energy, and you can find all the allowed states. And so here, these 2 dots are these 2 spins, and these red arrows correspond to the ordered states. So down here, we have this collinear state, and this is very analogous to what happens in the iron-based materials. And then here we have an interesting state where one site has a moment and the other has no moment. It turns out actually I found out these states actually exist. I thought they would not be very energetically stable, but they do exist. And then the state I'm interested in is this particular state here, where the 2 moments are orthogonal to each other. Now, we can classify all these states by the composite translationally invariant orders they have. And so in particular, this state here, this has a state which is characterized by S1 squared minus S2 squared is non-zero. So you can see S1 is non-zero, S2 is 0. This is a spin scalar quantity. And because inversion sits between the 2, this breaks inversion symmetry. So this is like some sort of multiferroic order parameter. And then this state here, well, we have S1 dot S2 isn't equal 0. This is inversion symmetric. This is also a spin scalar, so this is a monadic order parameter. And then here we have this S1 cross S2 is non-zero. This is a spin vector, and this is also odd parity because here we don't have here inversion. Clearly, these are not related by inversion, these spins. Okay, so I'm going to skip over this next bit here and come to the punchline. So in this state, we can ask about the symmetry properties of the spin vector odd parity state, S1 cross S2. It's time reversal invariant because S1 and S2 each individually break time reversal, but their cross product does not. It's odd parity, as I told you, because clearly this spin and this spin are completely different. And it's translationally invariant. And these are exactly the same conditions we use to write down a Rashba spin-orbit coupling. We break inversion symmetry, but no other symmetries. So in principle, this order can generate some spin splitting sigma z, up and down spins, f of k, where f of k is an odd function of momentum. And in fact, here's an example calculated now by a few people, which is the cerium, nickel, arsenic, and oxygen. I showed it earlier, but as a function of k goes to minus k, you can see that up and down are a switch. All right, so let me, how am I doing for time?
About 5 minutes.
About 5 minutes, okay, good. All right, so let me turn now back to this question I raised earlier. I've showed you we have this free energy. This free energy allows these states, and we can get this odd parity spin splitting. But the term I mentioned that is allowed by symmetry, but I haven't written down, is simply this term S1 dot S2. So this term typically appears with the 2 conditions I told you. It's inversion symmetric and it's spin rotationally invariant. And when we include this term, this forbids the existence of this S1 cross S2 because this pins the 2 spins to be parallel and also guarantees that the magnitude of the 2 spins must be non-zero, so this term is not allowed. So this term kills these 2 states, and the only state that exists is the collinear state. And so we have to ask, when does this term vanish by symmetry? And it turns out you can show that very generically in non-symmorphic space groups with the Q vector at the Brillouin zone boundary, so you're doubling the unit cell with those Q vectors, this term will vanish. A simple argument, I mean, the symmetries that do it are different for the different non-symmorphic groups, and so I can't say something generic, but what happens usually is you have some symmetry that takes S1 to S2, but then takes S2 into S1 in the next unit cell. But because we have this kind of pi-0 ordering, that one is related to the original one by a -1. And so S1.S2 goes to minus S1.S2, and that is an invariant in the free energy, and so it's not allowed because it picked up that minus sign under that symmetry. Now that we know this, we can actually do a very general group theory categorization of when we can get these kind of, or when this Ginzburg-Landau free energy is valid. And so we can classify space groups, wave vectors, and identify which representations for this was, for when this is right. And it's a job you can do by computer, and you find that there's 421 theories. This looks like a lot, but there's multiple Q vectors per space group, and so it's not as many as you think. And then you can also, because we have the group theory, we can determine the form of this f of k, and this f of k tells us what is the nature of the spin splitting in momentum space, and we find P, F, and H wave splits. And then, okay, in our paper we have tables which tell us the space group, the momentum points, and what kind of spin splitting in general you have. But I'm not going to dwell on that. And so then what we did after that is we turned to some DFT calculation and asked, are there materials in which there could be such a spin splitting that we can make a prediction for? And my colleagues had worked a lot on iron selenium, and it's well known that there in the 2 iron unit cell there's a pi-pi magnetic ordering that's very common. And then if we look at this coplanar state where there's 2 iron per unit cell, but these irons are these moments are orthogonal to each other. Our group theory argument said there must be this kind of H-wave spin splitting, and so we asked our DFT colleagues to measure how big is this H-wave spin splitting, and here's their results. So they went in yes, okay. Their result shows that it's actually relatively large. As you can see, it's on the order of 0.1 eV, so this is a very large energy scale. And so this is a prediction for this. It turns out this material doesn't show this particular magnetic order, but there is, this material does show this magnetic order when you replace the arsenic with phosphorus. And so in this region here, this magnetic state exists, and so we have a prediction that we should get this spin splitting in this magnetic state. All right, I must be running...
Yeah, 1 minute.
1 minute, okay. All right, so you can go through the Magen data. You can ask, where do we see these different kind of orders according to magnetic states that are found? Where do we find these odd parity magnets? Where do we find these multiferroic states? And so all these materials show it. Where do we find these pneumatic states analogous to the iron-based superconductors? And we have all these materials as well. So if we're interested in looking at pneumatic order or electronic pneumaticity, this might be a class of materials to look at and kind of repeat what we did for iron-based materials. All right, I'm going to skip the microscopic theory, and I'll just tell you the key results. We could ask, how big is this spin splitting? We have an exchange term J, which is the size of the magnetic order, and we have a hopping term T. The spin splittings are on the order of the square root of J times T, and so in principle can be large. All right. Okay, so I'm going to skip all this and then jump to my conclusions and take questions.
Okay, let's thank Katie again.